This clip is just an introduction to something called the Laplace transform, which is a concept in mathematics in itself, but it also has uses for ordinary differential equations, and that's why we're learning it. And it also has something called an inverse. And let's start with the definition. So suppose we have some function of g of t, and I want to mention that t is the usual variable we use when we take Laplace transforms as opposed to x. It's customary to use t. So the Laplace transform of a function, and it's denoted like this. This is some kind of a curly L. And what it is it's a new function, but in a different variable, s usually, big G of s. So the convention is that if we transform little g, we get big G, and little f would get big F, and so on. So we define as follows. So big G of s, which is the Laplace transform of little g of t, is defined as an integral from 0 to infinity e to the minus st g of t dt. The integral and the e to the minus st are always there. What changes is the function I put here, and that's our particular function g of t. Now notice that after we take the integral, we don't get t anymore because the integration is with respect to t, and what we're left with is a function of s. Also note that this is an improper integral, so sometimes we might have to put some number here and let it tend to infinity, or take the limit as it goes to infinity. Now this is all very abstract and theoretical, so we're going to need some examples. I'll bring two examples. In the first example, I'm going to show you that if we take the constant function, g of t is the constant 1, then its Laplace transform big G of s is 1 over s. And I want to demonstrate this for you. So big G of s, which is the transform of not the number 1, the function 1. So using the definition, and in our case, g of t is 1, so we put the 1 inside the definition from here, and this is the integral we get. Turns out this integral, which is an improper integral, converges when s is positive. So if s is positive, and you'll see why in a moment why I say positive. First of all, the integral of this is e to the minus st over the coefficient of t, which is minus s. S is like a constant here. Now when s is positive, then we get here e to the minus infinity when we let t go to infinity, and e to the minus infinity is 0, so the first part is 0 for the upper limit. The lower limit is 0, e to the 0 is 1, so we get minus 1 over minus s, and the minus with the minus will give us 1 over s. S has to be bigger than 0. Often we won't bother with the domain of the transformed function, but to be precise, we should say that this transform applies when s is positive. In our second example, we'll show that the Laplace transform of the function e to the t, the exponential function, is 1 over s minus 1. So let me demonstrate this. G of s is the Laplace transform of the function e to the t. And if you look at the definition, everything's the same except this part, which is where we put our particular function, little g. And now we have to do integration with respect to t. Using the algebra of exponents, we can rewrite this as 1t minus st, which is 1 minus st. What we have is the integral of some constant times t. I mean, as far as t goes, s is a constant. So it's just the exponent divided by this constant 1 minus s, taken from 0 to infinity. We're plugging in infinity, but we're really plugging in a very large number and taking the limit to infinity. This integral will converge for s bigger than 1, in which case 1 minus s is negative, and so a negative number times t as t goes to infinity will be 0. And when t is 0, we just get 1 over 1 minus s. So we get 0 minus 1 over 1 minus s. This is what we get, and as I say, this will be defined for s bigger than 1, although usually we won't be pedantic about writing the domain for s. And of course, there's plenty of solved examples after the tutorial. Now, of course, we don't want to keep doing the integral each time. There are certain functions that we often want the Laplace transform of, like 1 or like e to the t in our examples, And someone's done them already, so there's no point doing them again and again. So they've been put into a table. There are large tables, but here's a small table, a partial table, just to give you the idea of what a table looks like. On one column we have the function of t, and on the other side we will put the Laplace transform big G of s, and we just look it up in the table. So here's our example of g of t is 1, g of s 1 over s. We did this example. We also did this example in the particular case where a was 1, we had e to the t, and we got 1 over s minus 1. Now, as I say, sometimes you want to write the domain of these. Here we had s bigger than 1 in our case, and in general s bigger than a, but mostly we won't be that precise, and we'll omit this range for s. When you have an exam or a test, supposedly you'll be given a table larger than this one anyway. Now, we talked about tables of Laplace transforms, but that's not enough, because sometimes we have a variation of what's on the table and we need to know how to modify the transform. Let's look at the first rule and you'll understand. The first rule is written like this. The name of the rule is linearity. The Laplace transform is linear, which means that if we have a linear combination of two functions, g and h, a times one of them plus b times the other, then when we take the transform of that, we can break it up into two bits with a plus, and we can take the constants out. For example, suppose we want the Laplace transform of the function 4t squared plus 10 sine t. You won't find this exactly in the table, but you will find t squared in the table, and you'll find sine t in the table. According to the rule, this is what we would have. And now, as I say, we can look up these two Laplace transforms. The actual answer is not the point here, but I'll tell you that if you look up t squared, you get 2 over s cubed, and if you look up sine t, you get 1 over s squared plus 1. And then you do the computation, 4 times this plus 10 times this. That's not the point. The point is that we can split it up as follows. Okay, the second rule is that if we have some known function, maybe this function g of t is in the table, but we don't have this, we have some power of t, like t to the fourth times some known function, then what we do is we look up g of t in the table, and we take the Laplace transform, yeah, the wrong kind of L, the Laplace transform of it, and then this means the nth derivative of this function to just differentiate n times, and then you multiply by a plus or minus according to what n is. N is even, it'll come out plus, n is odd, it'll come out minus. So if we apply this rule, we get that the Laplace transform of t cubed sine 4t, which you won't find in the table, is going to be minus 1 cubed. Then the Laplace transform of sine 4t, but this has to be differentiated 3 times. I'm not going to do the whole computation, but sine 4t gives us, if we look at the table, 4 over s squared plus 4 squared, which is 16. But then we have to take the third derivative. This is prime, 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 meaning third derivative of this, and then multiplied by minus 1. And just in case you're wondering, you want to try it yourself, the third derivative of this comes out to be this. Minus 1 cubed is minus, so the final answer would be minus with the minus, and there we are, the transform of this. Now I want to talk about the types of exercises, and there's quite a few of them, and they're sorted according to different types. Exercises to compute the transform of a certain function using the table and the properties of the transform that we gave. We had 2 properties. After that, there'll be a couple of exercises where we have to compute the transform from the definition, and it usually will be piecewise functions. I mean, for example, that we have g of t is equal to t squared when t is less than 1, and the constant function 1 when t is bigger or equal to 1, for example. Then we can't use the table for this. We have to compute it directly. Then we'll have some exercises computing the transform of a periodic function, and I'll explain in the exercise what a periodic function is. But for example, sine t is a periodic function because it keeps repeating itself every 2 pi. And then finally, we'll learn to compute the transform of a step function, and I'll explain there what a step function is, or functions expressed using the step function, variations of the step function. And lastly, I just want to give you an overview of what this chapter contains. The chapter begins with the introduction, which is this clip, which we just did or are doing. Then the Laplace transform, mostly just exercises of how to compute Laplace transforms. Then we'll move on to the inverse Laplace transform. The inverse just means going back from a function of s to a function of t. So if I take the Laplace transform of some function g of t and I get big G of s, then the inverse Laplace transform, it's written like this with a -1 as a superscript, and I apply the inverse transform to big G of s, I've got to get back to little g of t. For instance, we showed that the constant function 1 has a Laplace transform of 1 over s, so if I apply the inverse Laplace transform to 1 over s, I should get back to the function 1. And then, and this is the most important, because we're in the course of ordinary differential equations, so we'll show how to use the Laplace transform to solve certain kinds of differential equations. Okay, that's it for the introduction and overview.